Inside the processor of a modern smartphone, microscopic transistors flip on and off billions of times a second. The electrical currents driving these switches are incredibly small, fractions of a fraction of an ampere. Compare that to the national power grid. To push energy across hundreds of miles of transmission lines, power companies have to step the electrical pressure up to hundreds of thousands of volts. Then there's the middle ground, the everyday devices we actually touch. A standard household remote runs on a completely different scale, needing maybe 3 volts to operate. If engineers had to write out the raw numbers for every one of these extremes, the math would become impossible to read. A single calculation could require tracking 20 or 30 zeros, turning basic algebra into an error-prone mess. And if a researcher in Tokyo uses a different term for a measurement than an engineer in London, they cannot collaborate. Complex systems fail when people don't speak the exact same technical language. Managing electricity worldwide requires 2 things: a universal baseline for exactly what property we are measuring, and a standardized mathematical shorthand for how much of it exists. That universal vocabulary is called the International System of Units, or SI. It ensures that engineers everywhere in the world communicate measurements the exact same way. Under this system, every distinct electrical property, whether it's the pressure pushing the electricity or the friction slowing it down, gets its own dedicated unit of measurement. This table breaks down electrical quantities. Current is measured in amperes, voltage in volts, and resistance in ohms. Each SI unit gets an alphabetical symbol, shown in the unit symbol column: A for ampere, V for volt, and the Greek letter omega for ohm. These assignments allow a factory technician, a university student, and a research scientist to all read the exact same electrical diagram without a single translation error. This leads to the golden rule of engineering calculations. A raw number written without its corresponding unit is completely meaningless. The unit provides the physical reality behind the math. But that still leaves us with the problem of scale. Knowing the correct unit doesn't help if you still have to write out 1 billion volts or 1/1,000,000th of an ampere. To solve this, we use engineering prefixes. A prefix acts as a simple multiplier. It scales the size of the measurement up or down without changing the base unit itself. Let's start with a baseline measurement of exactly 1 ampere. If we need to measure massive amounts of current, we can zoom out. Adding the prefix kilo multiplies that value by 1,000, absorbing 3 zeros. Mega multiplies it by 1,000,000, moving the decimal point 3 more spaces to the right. We can also zoom in to measure tiny fractions of an ampere. Moving the decimal point to the left gives us milli, representing 1/1000th of a unit, and micro takes us all the way down to 1/1,000,000th. Cautionary. This brings us to a common pitfall shown in this warning box. Because the prefixes just shift the decimal point, 1,000 milliamps is mathematically identical to 1 single amp. Ultimately, these prefixes are mathematical shorthand. By sliding the decimal point left or right, they keep global calculations compact, readable, and perfectly precise. Combined on a real-world schematic, we get a complete measurement like this: 10 kiloohms. The 10 is our raw magnitude. The lowercase k is the scale prefix, multiplying by 1,000, and the omega symbol tells us the property is resistance. Together, these 3 components, the amount, the scale, and the property, form a complete scientific statement that any engineer on Earth can instantly understand. Learning this system gives you fluency in the actual language of modern technology, allowing you to read schematics as easily as sentences. To accurately read, design, or troubleshoot any circuit, you have to know the unit, apply the correct prefix, and write every measurement completely. That is how the physical world gets built.